stereochemistry. And so we're going to do that. It's going to be fun. All right, so changing gears a bit. All right, so we've drawn all of our molecules. We've pretty much drawn them all flat, right? And you got some sense of there being some depth to them with the chair conformations, right? That there's actually a three-dimensional shape, and some of the groups, some of the carbons are forward, some of the carbons are away from you, right? So stereochemistry deals with us thinking about molecules in 3 dimensions, right? So this leads to there being isomers. So let's talk about what isomers are. Right, we've already kind of touched on this some, right? But it's always good to review, especially, you know, now since you guys cannot see me for like 3 weeks. It's weird, right? So isomers are compounds with the same formula but different structures. So we talked about this extensively with constitutional isomers. Right, with constitutional isomers, the atoms are bonded in different orders / arrangements. Right, so if we have C4H10, right, you can have butane, or you can have 2-methylpropane. Whew, that was really bad, right? Or if you have C5H12, right, you can have pentane, 2-methylbutane, there we go, and 2,2-dimethyl propane, right? So these are constitutional isomers. The atoms are arranged in a different order. The way the bonds are put together is different. You have different bonding, right? And then there's another type of isomer that are called stereoisomers. The atoms are bonded in the same order, but are displayed in different I'm blaming the pen, that's not me. I mean, I did not have a stroke. Trying to think of the right order. Different 3-dimensional spaces, I guess. I guess is the best way to do it here. Right. So all the bonds are put together the same way. You would name the molecule the same way, but how the groups are arranged in space is different. Right? So we have, of these, there are 2 types. Right? If you're looking at the slides, you'll see these as well, right? So there's conformational isomers. So conformational isomers, think about like Newman projections. right? So I can have butane versus butane, right? If you make the Newman projection, I guess I'll make my Newman projection this way, right? Ooh. Sorry, that is backwards for that, so let's fix that. Like you're getting all like the sweet class action. Like me like messing up. I'm not swearing, so that's good. Right, so try that again. So, right, because that methyl group would be down if I'm looking at that. Right? So this is the anti-conformation. And now I have this drawn as the eclipse conformation. Right? So they're the same molecule, they're both butane, but how these two methyl groups here and here are arranged, right? Down and up versus both being down, right? The arrangement of the molecules in space is different in that these are conformational isomers. Similarly, right, if you think about chair conformations, right? This versus this, right? So these are two different conformations. These are stereoisomers. They are conformational isomers. They have the same name. It's ethyl cyclopropane. No, sorry, ethyl cyclohexane. But the arrangement of the methyl and the ethyl, sorry, the arrangement of the ethyl group here, equatorial versus axial here is different. Right? So they're conformational isomers, but they have the same name. Right? So those are conformational isomers, and something that, so conformational isomers can interconvert. By rotating, well, I can't say that one. By rotating single bonds, right? So we can get from, sorry to jump back, we can get from this anti-staggered butane to a fully eclipsed butane just by rotating around this single bond right here, right? We just turn around that bond, turn around this bond right here, make a better arrow, and we can get from there, we can get from here to here by rotating around that bond, right? Similarly, we get from here to here, or we get from this chair to this chair, right? We pull this carbon up, these bonds rotate a little bit. We pull this carbon down, again, these bonds rotate a little bit, and you get your product, or you get your different conformation, you get a different isomer. So we can go from one isomer, conformational isomer to another, just rotating single bonds. The other type of stereoisomer are called configurational isomers. So configurational isomers cannot interconvert, right? To go from one configurational isomer to another, right, a bond must break. Right? So if you have a flask that is one configurational isomer, it will stay that configurational isomer forever because you can't get from one to the other. So there are some examples of this. One's kind of a sneak peek. So we have cis, trans for double bonds. Wow. Right, so if we have a double bond, right, this is the trans isomer. Did these in the wrong ones, right? Right, so if you look at it, my two methyl groups are on opposite sides of this double bond, right? Double bonds can't rotate, so these two methyl groups will stay on opposite sides from each other forever. Right, now there's the cis. Right, and the cis isomer, now my two methyl groups are on the same side of the double bond. This is the cis. And if I have a flask of cis and another flask of trans, they will always stay cis and always stay trans. They can't go from one to the other. But again, if you were going to name this without worrying about the double bond, right, they would have the same name. The only thing that's different is where those two methyl groups are. There's cis and trans in rings. Right, and this is similar. Right, so if I have a ring, I'm going to get a little artsy here. I have a ring like a cyclobutane. Right, I can have groups on the same side. These are cis. They will never become trans. No matter how I flip the ring, if I try to do like a ring flip or whatever, they're always going to stay on the same side. Now if I have the same thing, okay, I'm going to put a little verse in here. All right, now, let me get rid of that extra bond. One, not really a bond, but you know what I mean. Get rid of this guy, not my best drawing. There we go. Helps way better. Okay, so if I get rid of okay. So now this is trans, right? My two groups are on opposite sides. So here, chlorine and my methyl are on the same side. They're both up. Right? If we look at this ring, here my chlorine and my methyl are on opposite sides. One's up and one's down. And they will always be up and down forever and ever. Right? So I'm going to jump ahead a little bit here, because I always end up doing this. Let's get so into it, I just talk about it without it. So the last thing that's a little bit different are chiral centers. Right? So that is the third type of stereoisomer we need to worry about. Right? And a chiral center is a carbon that is bonded to 4 different groups, which is single bonded. So it's a carbon with 4 single bonds to 4 different groups. So what I mean by different groups is no 2 groups can be the same, right? So it's not like right? This is not chiral because I'm only bonded to 3 different groups. So I have 1, 2, and then these hydrogens aren't the same, so it's only bonded to 3 different groups. Now, if I have fluorine, chlorine, hydrogen, and a methyl, now this is chiral. I'm going to try to make that look like letters, sorry. That is chiral because I'm bonded to 4 unique groups, right? That carbon, I have 1, 2, 3, 4 unique groups on that carbon, right? So a carbon that is bonded to 4 different groups is chiral, right? So these are sometimes, so a carbon like this is called a chirality center. Okay. Sorry, folks. I'm like, I'm going to write with my finger. And then it looks terrible. So these are called chirality centers. Or stereocenters. Or sometimes just chiral centers, which is what I usually will normally say, or chiral center / chiral carbon are the terms I will use, or you'll sometimes hear stereogenic. Center. So those are your kind of what those are called. Right. Now, so what's interesting is when you have a chiral carbon, every compound that has 1 chiral center can exist as 2 different isomers. These 2 different isomers are non-superimposable mirror images, right? They can't lay on top of each other and have everything match up perfectly. Right, so see what I'm talking about here. So let's say I have a compound that looks like this. Now I'm going to put a wedge and a dash. So just to refresh, we type about this briefly. So a wedge means that the group on the wedge is pointing out of the screen at you. You can think about it sticking straight out of your screen at you. Right? And then, so this group here, is out / up. Right? And then we have a dash. A dash means that group is pointing away from you. So this is away / down. Right? So the other isomer, let's say we put a line here, and let's say this is a mirror. And we're going to reflect our molecule across that mirror. Right? So the methyl group, right here, that methyl group is closest to the mirror, and the hydrogen is farthest from the mirror. So when we draw it, methyl group's going to be close to the mirror, hydrogen's going to be far. Right? And now we're going to have our fluorine and our chlorine. So the fluorine and the chlorine, it doesn't matter if they point left or right. So when I say they're on a wedge and a dash, that fluorine is sticking straight out, is in the plane of the mirror. So if this mirror is coming out and back, right, out of the page and then into the page, the fluorine and the chlorine are on that same, are parallel to that. So the fluorine is sticking straight out, the chlorine is sticking straight back. There's no like tip left or right to the fluorine and the chlorine, right? So these two molecules now I have drawn, these are two different isomers, right? So these here, these are stereoisomers. They have the same formula, right? But the way the atoms are arranged is different, right? And it might be hard to see, right? But if we were to take and try to slide these two molecules over, right? I could slide these over and the fluorines would both point out, the chlorines would both point back, but on the left-hand side, I'd have a hydrogen here, and on the left-hand side of the other molecule, I have a methyl group. So when I slide them on top of each other, the fluorines and the chlorines line up, but the methyls don't line up, right? Methyl covers hydrogen, and hydrogen covers methyl for the two isomers. If I grab this molecule and I flip it over, I can flip it so that the hydrogens and the methyls line up, but when I flip it, when I take it from facing this way and flip it over, the fluorine goes from pointing forward to pointing back, and so the fluorines no longer line up. So what I need you to do now, I need you to humor me, right? I need you to hold up your hands. Your hands are enantiomers, right? Your hands are non-superimposable mirror images, right? If you hold up your hands, right, your thumbs, if you hold your hands so your thumbs both point in, right? You can put your hands on top of each other so that the palms line up, the palms overlap, and the back of your hands overlap, but then your thumbs don't overlap, right? You can flip your hands over so that your fingers all match and your thumbs line up, but now you have your palm to palm and back, and the backs of your hands are facing away from each other. So you can't line it up so your hands are flat, that your palms match, in the backs of your hands match with your thumbs overlapping. So this is an example, and I said it not thinking, these type of stereoisomers are enantiomers. Right? They are non-superimposable mirror images. Right? Enantiomers are chiral molecules. Have no symmetry. All right, so if you look at it, so we look at my example here, fluorine, chlorine, H, there's no way, there's no place I can put a plane that if I try to do this and go across the fluorine and the chlorine, my hydrogen and my methyl don't match. So this and this don't match. If I try to, how did it work? If I try to put a plane of symmetry in the plane of the board, so I cut my hydrogen, my methyl in half, my fluorine and my chlorine don't match up. So a chiral carbon has no symmetry. A chiral molecule has no symmetry. A chiral molecule, so A space chiral molecule, so a molecule that is chiral has no symmetry. Achiral, all one word, molecules, so molecules that are not chiral have symmetry. It's a little weird, but you'll get it. All right, so the thing I need to get to, I don't know if we're going to be able to get there. Oh no, we'll see. We'll see, we might have to like add something here. So how can we draw an enantiomer? Right? So, I'm blanking on perspective right now. Wedge dash is kind of what we, no, perspective is this. Perspective is what I always draw. So perspective is you have the wedge and the dash. Right, so here when I draw this OH, this hydrogen is understood. So if the OH is 4, the hydrogen is understood and it is back. Right? There's wedge dash, so this is perspective. And the wedge dash is, make sure I do this right. This is old-timey. So wedge dash you've tipped your carbon kind of on its side. So basically you take this and you tilt it back away from you. So these two groups both point back. So the groups that are up and down are back. And the groups that are horizontal are up. So you kind of tipped the carbon on its side. And this is wedge dash. Right? And then the last one are Fisher projections. And Fisher projections suck. Fisher projections are basically, if you look at wedge dash drawings from space, so, right, instead of having the wedge and the dash, we get rid of that and we just have lines. And it's the same structure that we had before, right? So these groups here, sorry, I didn't match my colors. These groups here are back, right? So the vertical groups are back, and the horizontal groups are up. So it's basically like you took your wedge dash drawing and you smushed it. And instead of having the wedges and the dashes, you just had them flat. Right? So we have to be able to name enantiomers. So we have to be able to distinguish enantiomers. So we do this through a system called R and S, right? So you can have, so naming enantiomers, right? You have R and S. So in a pair of enantiomers, so we're going to go back to the drawing I had before. That is not a thing here. Let me pick a different one. All right, let's pick an easy one here. One in every pair, you have an R and you have an S. R is for levorotatory, and S is for sinister, or sorry, rectus and sinister. There we go. And sinister is left because left-handed people aren't to be trusted. So the reason left is sinister, right? So is because it used to be when you would shake hands, you give your right hand, you're like, hey, here's my sword hand, here's my stabbing hand. And left-handed people would be like, here's my stabbing hand, oh, not really, and can still stab you. That's why left-handed people aren't to be trusted. So how do we assign RNS? Right, we have to assign priority. Oh wait, I think I gave myself an hour. I can slow down, I'm sorry. I gave myself an hour for this, not 50 minutes. I was really panicking. All right, we're gonna assign priority to groups. All right, so priority is assigned basically, not molecular weight. It's assigned by highest atomic number is the best way to kind of think of it. Right, so let's say we have our chiral carbon, right? The way I'm always going to draw these, I'm always going to draw them in perspective. So just kind of settle in, right? Is I'm going to put the fluorine in here. I'm going to draw it a little bit differently. Right, so the way we can assign priority is we assign it based on atomic number. So what has the highest atomic number? We have to compare, so we look at this carbon and we look at each atom coming off of it. So we're going to look at the chlorine, the hydrogen, the fluorine, and the carbon. So of those four, chlorine, fluorine, carbon, and hydrogen, what has a higher priority? Chlorine does, because chlorine has the highest atomic number. Right, so this gets priority 1. Of what's left, what has highest priority? Fluorine is 2, because fluorine has a higher atomic number than carbon. Then carbon is 3, and hydrogen is 4. Hydrogen is always 4, because hydrogen is the smallest, lightest atom. So we assign our priority, and then we play connect the dots, right? So after we do assign priority, you connect 1 to 2 to 3. And the direction that you go 1, 2, 3 determines if you go R or S. So we can just ignore 4. So we go 1, 2, 3, 4. So there we connected it kind of clockwise, right? So I don't know where that P came from. That was awkward. Sorry, I kind of turboed that little section because I forgot how much time I gave myself. So with the low priority group on the dash, R is clockwise, S is counterclockwise, right? So this, we went 1, 2, 3, 4, we went clockwise. So this carbon is R. So I'm going to draw that one again. Now I have time. Oop, nope, same way, sorry. Great, so now if I draw its mirror image, right? We've assigned priority 1, 2, 3, 4. This is R. The enantiomer, the mirror image, 1, 2, 3, 4. The enantiomer has to be the other designation. So here I go 1, 2, 3, 4. I go counterclockwise, and that becomes S. So, let's do another one. Right, so if we look at this, we assign our priority. Bromine has higher priority than oxygen. Right, contrary to that, bromine has higher priority than oxygen because bromine has a higher atomic number. So we go 1, 2, oxygen has a higher priority than carbon. 3, hydrogen is 4. So we can connect the dots. 1, 2, 3. This is R again. Now, when we have groups that are the same, it's a little tricky, but not really. So again, we're going to compare all the groups on our chiral carbon to determine if it's R or S. So we're going to look at this carbon, right? And we're going to work our way. So we're going to say, okay, I have a carbon, a hydrogen, and an oxygen. Well, of those, oxygen has highest priority, right? Because oxygen has the higher atomic number, so this is 1. Now, the, what's it called? Now, comparing carbon, and hydrogen, we know hydrogen has the lowest priority, so it's 4. So now we've got these 2 carbons and they're tied. So what we do is we walk down the chain. So here we're comparing a carbon to a carbon. So now we go to the next atom to try to break that tie. Yeah, we'll leave that there. So what's our next atom? We have a hydrogen sticking out here, and our next atom down the chain is a carbon. So now we're comparing this hydrogen to this carbon. What has priority? The carbon does. So now our carbon's going, so this whole chain is going to be priority 2, and then this methyl group is priority 3. So again, I miraculously ended up with 1, 2, 3. I ended up with R. Right, so So here, again, I'm looking here, and I'm going to compare chlorine to a carbon, and a carbon. Chlorine has highest priority. Now, I have 3 carbons, so I have to try to walk out in such a way, walk out the chains to break the tie. So on this carbon, the next thing out is a hydrogen. So the next thing out here is a carbon, next thing out here is a carbon. So I'm comparing hydrogen to carbon to carbon. Hydrogen loses, so hydrogen is 4. But now I have 2 carbons that are tied. So now I have to go in such a way, I have to move down the chain in such a way to break that tie. So if I'm looking at this carbon here and this carbon here, if I go to the end of the chain here and here, I compare carbons and I'm still tied. But I can also say, hey, what if I go down this carbon, right? So now I have a carbon there, and I'm comparing a carbon to a hydrogen. This carbon wins, so this makes this whole chain 2, and this chain 3. So then I connect the dots, 1, 2, 3, and it's S. Now, it might be hard to remember R and S, right? Right, so R is clockwise. When the low priority group right, 4 is back slash the wedge, right? And a way you can remember this is that when you make, as long as you're not like some sort of monster, when you make an R, the first curved arrow, curved line you make goes clockwise, right? So R clockwise, S is counterclockwise, right? Again, when the low priority group 4 is back or on the wedge, and remember that is the first curved line you make. When you make an S, is counterclockwise, unless you start at the bottom and like get out. Like, who starts at the bottom for their S's? It's uncalled for, right? So make an S that looks less crappy, right? So if you have your S, the first line you make is counterclockwise. Right, so I want to show you how to draw enantiomers a different way. So let's kind of go back to, right, so we'll have that. And then drawing enantiomers like this, right? And if we assign R and S, right, this is 1, 2, 3, you make 4. That is counterclockwise, so that is S. I don't know, my S looks upside down, but it's an S. 1, 2, no. Sorry guys and gals. Try this again, because this is hard. 1, 2, 3, this is 4. We can go counterclockwise, that's R, right? We can also draw enantiomers instead of having to like mirror plane the whole thing over. What you can do is you can just switch what's forward and back. Cl, F, we'll put the OH back and the hydrogen forward. So all we've done is we've switched these two groups, and now these are enantiomers of one another. And hopefully we pick up the next set of slides, or the next video. We'll pick this up. We'll have more examples of R and S at the beginning. You may notice that there is a totally different style happening here. And that's because these two videos, or this video is made up of two videos, one that was filmed a few years ago and one that is filmed now in the time of the Rona. So what I want to do is I just want to finish off this lecture to kind of get a full 45 to 50 minutes, and then we can go from there, hopefully in person in class. So the first thing I want to do is I noticed looking at the video that you were just watching, there was a slight mistake. So I want to fix it real quick, and that is that R, right, is clockwise. When the low priority group, even after all this practice, I still can't write on a screen. group. So your low priority group, your 4 is back slash, I did it again, slash on the dash, right? On the, what you just watched, it said back slash wedge, but the wedge is forward, the dash is back. I just wanted to fix that. So, S, as he messes it up, right? S is counterclockwise. When low priority, your 4 is back slash on the dash. So it doesn't really change anything that you kind of stuck in your head. I just like goofed when I wrote wedge and dash on that one slide. So I just wanted to clear that up before we moved on. So we left off in that little bit about looking at, let's say we have a compound like this, and we want to draw it as an enantiomer. And the way that I had first shown you was you just basically reflect the compound across a mirror plane, right? And if we check, right, the oxygen is going to get highest priority here, right, because we're comparing an oxygen, a carbon, and a hydrogen. We know that the hydrogen is going to get the lowest priority because hydrogen is always low priority. And then we have 2 carbons to compare. And so we have a carbon here and a carbon here. Those are tied, so we walk out a group. So the next group here is a hydrogen. The next group on this side here is another carbon. So now I'm comparing this carbon to this hydrogen. So this carbon over here has priority over the hydrogen. So this becomes 2 and this becomes 3. So we can connect the dots 1, 2, 3, right? And we're going clockwise. So this side's R. If the other side is the enantiomer, it should be S. So we're going to have 1, 2, 3, right? Hydrogen is going to be back. So this is going to be 4. So 1, 2, 3, like that. And this goes counterclockwise, so this is S. So they're enantiomers. But we can draw these another kind of quicker way, and that is to make an enantiomer, you only have to switch the wedges and the dashes. So let's do that same thing again. All right, so what I can do is this, and then this compound. These are enantiomers. They're non-superimposable mirror images, right? So here's where we have to do a little bit of mental Tetris, and you can see how this compound is the mirror image of the one I just gave you, right? So here our hydrogen is back, our hydrogen is forward. This is where doing this like not in person is hard because I usually like throw my hands around like a crazy person right now. So you can think of this as having your mirror above the molecule on the left. So you could think, okay, make a different color. This molecule right here, the yellow box bracket around it, if I put the mirror on top of it, that reflects to this compound here. Another thing you can do is what happens if we take this molecule, right, and we grab this and we just flip it. We just pick it up and we flip it over. So if you were to just flip this, right, where you would pull it up out of the page and have it flip over, it would look like this, right? It would be the mirror image of the molecule in the yellow bracket. Right, so we have to, the other way we can check this, right, to make sure that I'm not lying to you and saying that the green molecule in the green bracket is the enantiomer of the molecule in the yellow bracket, is we have to be able to assign R and S. You don't know how to do that yet, so let's learn. All right, so what I do is when the low priority group, when the 4 is on the wedge, you do everything you do for when the low priority group is on the dash, but at the very end, you switch your configuration. So I always end up saying a lot, looks R is S, or looks S is R, right? So all of the rules for this, for determining R and S, are built for you to be standing, if you will, so that the low priority group points away from you, right? And when you're standing on the wrong side of the molecule, everything's backwards. So you just have to realize, hey, I'm standing on the side of the molecule that the low priority group points toward me. So now I just have to realize I have to flip everything, right? It'd be like if you looked at a clock. If you look at a clock, right, you know what direction clockwise is. But if you had a clock that was clear and you were on the other side, right, clockwise would look backwards to you, not because the clock's doing anything different, just that your perspective has changed. So how does this kind of play out? So let's do this example again. Right, we already assigned all the priorities. Super easy. 1, this is 4, 2, and 3. 1, 2, 3. Right, low priority group points away from me. So that means that this goes clockwise, so this is R. Now I'm going to draw it where I switch the wedge and the dash. Right? So we already know all the priorities. 1, 2, 3, hydrogen makes 4. Right? So now I connect the dots. This looks like it should be R, but the low priority group points at you, so it's actually S. Right? So you realize you're on the wrong side of the molecule, so you have to go, oh, I have to switch this because the low priority group's pointing at me. Right, so that's the same as if you had done it like this, where you flipped the mirror image, right, where you took this molecule here and had it and did it across the mirror plane like we did a second ago, right? Here's my low priority group 4, right, S. So these two molecules, here and here, these are the same thing. You've just kind of changed how you're looking at them. All right, so let's bang out a few more examples here. Put an oxygen here. All right, or we could do something like this. Great, and this one here has a lot more going on than you've seen before. All right, so let's assign priorities to the one with the bromine. So we have 1 chiral carbon, that's right there. And so we're comparing bromine, oxygen, carbon, and this hydrogen here. So we know that hydrogen is going to be our low priority group. We know that now we're comparing oxygen, bromine, and carbon. Bromine has a higher priority because it's heavier. It has a larger atomic number. So this is going to be 1. This is going to be 2. Carbon's going to be 3. Right? 1, 2, 3. This looks like it is R. Sorry, it looks like it's S, right? It looks counterclockwise, but the low priority group's pointing at you, so it's actually R. Here, right, we have chlorine and a bunch of carbons. This chlorine gets high priority. Now I'm comparing carbon, carbon, and carbon. These are all tied, right? So if we go out one atom here, this goes to a hydrogen, this goes to a carbon, and this goes to a carbon. So these are still kind of tied. So what I like to do is say, okay, how can I break the tie as quickly as possible? So this carbon is also bonded to a hydrogen. So I could go, now I'm comparing hydrogen to this carbon. This carbon has priority. So then this will be 2, right? And now I'm comparing this carbon to this hydrogen. This will be 3, this will be 4. All right, 1, 2, 3. This is counterclockwise. So this is going to be S, right? So you don't always have to have hydrogen as your low priority group. Anything can be your low priority group. It's just where it is compared to everything else, right? So here I have 2 chiral centers, so I'm going to do them one at a time, but I can assign both of them R and S. Right, so let's start with the green one here. Right, so we're comparing chlorine, carbon, carbon, and carbon. So chlorine is going to be our highest priority group. So now we have to compare, excuse me here, this carbon, and this carbon to figure out what is our second priority group. So again, carbon, carbon, and carbon were all tied. We walk out on this carbon, we have a hydrogen, right? This carbon here, and this chain here, and this chain here, the next group out is a carbon. So let's break the tie as quickly as we can. We can say, hey, this carbon has a hydrogen, this carbon has a bromine. So the bromine takes priority over the hydrogen. So we're gonna say that the chain with the bromine is 2. We're gonna actually pick the right, stick with the same color here. Yeah, 2. This is 3, and this is 4. So here the methyl group is our low priority group. So 1, 2, 3, counterclockwise again. But the low priority group points at me, so this is R. So we'll look at the group with the bromine. We'll use baby blue. So we're going to look at this carbon now. Bromine is our high priority group. Here we have a hydrogen, that's our low priority group. Here I have a carbon against this whole big chain. The big chain wins, 2 and 3. Again, this looks S, low priority group points at me, is R. Right, so I keep saying you want to break the tie as quickly as possible. So let's do this. Right. All right. So what I'm doing here is if you've got 2 chains that are kind of the same, but there's a branch. So here I'm comparing this carbon and this carbon to assign priority. Right. We already know that this is 1 and this is 4. Sorry for the baby trying to help out there in the background. So when you have 2 chains, and one has a branch and one doesn't, you can use that branch to break your tie more quickly. So you can look at this, right? This one here and this one here and say, okay, I'm comparing carbons here and here, but we'll make it the green carbon here. It has a branch on it. So I can just say, hey, if I go off the main chain, I'm going to have a hydrogen that I'm going to compare to this carbon. So that carbon is going to give you the higher priority. So you're going to say, hey, this has 2 priority, this has 3. So then 1, 2, 3, this is S. Right? Now, similarly, right, you can have a longer chain, right? And let's say we've got H and then, right, something like this, where again we know 1 and 4, right? Oxygen has priority over carbon and hydrogen, so that's 1. Hydrogen has priority over nothing, so that's 4. So now again I need to compare this yellow carbon to, make this green carbon. All right. So looking at those, right, it doesn't matter that this green side is longer, right, because you're only looking atom by atom. So we can get here and we can say, well, yellow carbon's a carbon, green carbon's a carbon. If I go out, I have a carbon here and a carbon here, so it's still tied. But you can go another way and you can compare the carbon on the branch to basically there's just a hydrogen here. So now I'm comparing this carbon to this hydrogen. So then the yellow carbon gets priority, so this is 2 and 3. So you can go 1, 2, 3. This looks S is R. So what you really want to do is you break your ties by where branches happen first. Now, if you have branches that are the same, right? Let's say, again, let's put something like this, right? Right, we're looking at this carbon here, right? So we know oxygen is 1, carbon, 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 all tied. If I go out here, I have a hydrogen, a carbon, and a carbon. So we know that the methyl group has lowest priority, so that's 4, right? And now we're comparing yellow carbon and blue carbon here, right? They both have a branch in the same place. So now let's just do it based on if the branches are different, right? So now we're comparing bromine to chlorine. Bromine takes priority over chlorine, so that means this chain takes priority over this chain. 1, 2, 3. It looks like it should be R, but the low priority group points at me, so it is S. Right, and we could do the other groups as well. Right, so this is 1 for here. We have a hydrogen on a wedge, so that's going to be 4. And then we have this carbon versus this carbon with a branch, so we know the green dot carbon that we have here is going to be second priority. It's going to be third, so this is 1, 2, 3. Luxar is S. Our yellow carbon, chlorine is 1. Green dot carbon is 2. Ethyl group is 3. And then this hydrogen will make 4. 1, 2, 3. Looks like it should be S, but the low priority group points at me, so it's R. Right? So that's how you, 1, use branches to break ties, and 2, just what happens when the low priority group is pointing at you. So the last thing we need to talk about is what happens when that low priority group isn't on a wedge and isn't on a dash, right? So we can do this, right? Low priority group is on a dash, no big deal. We can do this. Low priority group on a wedge, no big deal. But what happens if our low priority group is on like in plane? It's not on a wedge or a dash. How do we do that? Right? Our rules are for low priority group away from us, low priority group towards us. How do we do low priority group in plane? So I like to say we're going to redraw and switch. Okay, so how does this work? Great, so let's take this. Sorry, my H is a little ugly there. All right, now I'm going to redraw it. Right, what I want to do is I'm going to put the low priority group on the dash, right? So what I'm going to do is I'm just going to take this, I'm going to switch whatever the low priority group is, in this case the H, with whatever on the dash. So in this case, the dash has a methyl group, right? It has a CH3. So if I switch that, right, you can do the RNS of this new compound. right? So we could say, okay, 1, 2, 3, this is 4. This compound is R. So the trick here is when you take two groups on a chiral center and switch them, right? You take that in-plane group and you put it on the dash, and you take the group that's on the dash and put it on in-plane. These two compounds are enantiomers. Right, so whenever you switch any two groups on a chiral carbon, you make the enantiomer. So since these groups are enantiomers, we made the easiest possible version to do the chirality of, right? We put the low priority group on the dash. So that was R. Since these are enantiomers, this means we started with S. So we know that this is S because the one that we redrew was R. So we redraw it, we get an R, and we switch it back to the beginning one, and it's S. So just like, right, so I already showed you this, right? You take this, you switch the group on the wedge and the group on the dash, right? Doop, doop, doop. Right, you know these are enantiomers. Right, same thing. Right now, just like we did a second ago, you have this. And then you switch this group and this group. You just switch two groups on the chiral carbon. These two molecules are also enantiomers. Right, so anytime you switch two groups on your chiral center, you're going to make enantiomers. So whenever your low priority group is not on a wedge or a dash, just switch it to the other side. Switch it to being on a dash. And it's going to work out super easy. We're going to do some more examples next lecture. And we'll do some ring examples, and then we'll kind of move forward from this. But you have all the basic rules to be able to assign R and S to most structures. So I will catch you next time.